All right, welcome to The Explainer. Today, we're going to unlock a really fundamental principle engineers use to design, well, everything, from rockets to hydroelectric dams. It's all about harnessing the incredible power that's hidden inside flowing fluids. So what do I mean by that? Let's kick things off with a little puzzle. So what on earth could possibly link the gentle swimming of a jellyfish, the raw power of a rocket launch, and, a simple garden sprinkler? Well, the answer is this really powerful idea. You can create a force, a push or a pull, just by changing how a fluid is moving. Now, to get how this works, we've got to go back to a name we all recognize, Isaac Newton. The principles are exactly the same ones that describe a baseball flying through the air, but we're going to look at them through the eyes of a fluid dynamics engineer. The first key idea we need to grab is linear momentum. And at its heart, it's a wonderfully simple concept. If something has mass and it's moving, it has momentum. The heavier it is, or the faster it's going, the more momentum it has. The slide calls it mass in motion, and that is the absolute perfect way to think about it. Now, you probably remember F equals ma from high school physics, right? But for engineers who are dealing with fluids all day, it's way more useful to reframe that idea. The net force on something isn't just about acceleration, it's equal to the rate that its momentum is changing. And that is the crucial bit, because in things like a jet of water, momentum is changing constantly. So how do we actually apply this? Calculating the force on something like a pipe bend seems impossible, right? If you had to track every single water molecule zipping through it. But this is where engineers get really clever. They completely rethink the problem.
No, seriously, think about it for a second. Trillions upon trillions of molecules, all bouncing around, trying to follow one specific blob of water as it moves and twists. It's a mathematical nightmare. It's just wildly impractical. So engineers came up with a much more elegant solution.
Instead of trying to follow the fluid itself, they just draw an imaginary box around the thing they care about, like that pipe elbow. This box, it's called a control volume. And instead of worrying about everything happening inside the box, they just measure the momentum of the fluid going in and the momentum of the fluid coming out.
And this is just a brilliant illustration of how powerful that idea is. The difference between the momentum flowing out and the momentum flowing in, well, that tells you the total force that's acting on whatever is inside that box. So by picking your imaginary box smartly, you can just ignore all the crazy complex chaos happening inside and get a clean, simple answer for the forces you're looking for.
Okay, so let's see this thing in action. How does this imaginary box help us calculate real-world forces? Like the force you'd need to bolt a pipe down to the floor.
So take a look at this pipe elbow. Water flows in horizontally, just full of momentum. Then the pipe forces that water to change direction, maybe go upwards. That change in momentum puts a force on the elbow, trying to shove it away. And to keep that elbow from just flying off its hinges, you need an anchoring force to hold it steady. And our control volume method can calculate that force perfectly.
And get this, as this table shows, the angle you deflect the flow, it matters a lot. Look at how dramatically that force changes. Just a 30-degree bend needs over 2,000 newtons of force to hold it down. But if you reverse that flow a full 180 degrees, the force just shoots up to almost 2,600 newtons. It's such a powerful demonstration. The more you change the momentum, the bigger the force you have to deal with. So far, we've only been talking about linear forces, pushes and pulls. But this very same principle can also create rotation, or what engineers call torque. And to understand that rotation, we just need one new term, angular momentum. And just like linear momentum is mass in motion, you can think of angular momentum as mass in a spin. It's just the rotational version of the exact same idea we've been talking about. And this takes us right back to our garden sprinkler. Water flows from the center, out through the arms, and then jets out sidewise. From the point of view of that central pivot, this creates a huge change in angular momentum. And guess what? According to Newton's laws, that change creates a torque. And that torque is what makes the sprinkler head spin around and around. Okay, so we've got pushing forces from changing linear momentum, and we've got spinning forces from changing angular momentum. But why is this so important? Well, because this single principle is the secret sauce behind countless technologies we use every day.
A rocket works by throwing gas out the back at an insane velocity. That's a massive change in momentum that creates thrust. A wind turbine works by literally stealing momentum out of the air. A centrifugal pump spins to fling water outwards, adding angular momentum to build up high pressure. Even a jellyfish swims by pushing water out from under its bell, changing the water's momentum to push itself forward. It is absolutely everywhere.
So the key takeaway is this. By understanding and controlling how a fluid's momentum changes, we can generate these incredibly useful forces, from a manta ray gliding through the ocean to the engines on a jet plane. It's all about getting force from flow. So the next time you see a fan spinning or a sprinkler watering a lawn, think about that little imaginary box and ask yourself, where is the momentum changing? Because once you see it, you'll find this secret weapon everywhere. Thanks for joining us.